The second problem is this one, where you are asked to draw the shear and moment diagrams for each of the three members of the frame. Assume the frame is pin connected at A, C and D. So it is pin connected here A and C and D, and it is fixed at B. So let us see how can we solve this frame problem. So let us copy this one. So A is spin, C is spin and D is spin. A, C and D are pinned. And B is a fixed support. Okay, so that is what given here. B is a fixed joint. B is a fixed joint. So now if you look at this first step, we have to see whether we can solve this using statically determinate as a statically determinate frame using standard equilibrium equations. So if you look at A, it's a pin, so there is a RA and then there is a HA and then there is RD and then there is HD. So if you take equilibrium equation you can find RA plus RD minus 50 and 40 0. There are no other forces acting in the vertical direction. If we take horizontally, HA minus HD minus 15 into 6. 15 into 6 is 0. Then if you take moment at A, RD into the distance to D from A is 2 plus 3, 5. RD into 5 minus 1.5 into 50, so that's 50 into 1.5 minus 40 into 3.5, that is also clockwise. Then the effect due to this is going to be at 3 meters. So 3 meters is 1 meter above from this, so that is counterclockwise. So plus 15 into 6 into 1, because it is acting at 3 meter from D, and since this is 4 and this is 2 meters, then it's 1 meter. So 15 into 6 into 1. And you need to also consider the HD. HD is going to be a clockwise moment, so minus HD into 2 is 0. So these are the three possible equilibrium equations we can derive. And can we solve this unknown? how many unknowns we have? We have RA, RD, HD and HA. So 4 unknowns, 3 equations. So we can't solve as it is. But since C is a pin, we have an opportunity to solve this in a different way. So what we can do is we can break this as 2 components. So the first component is this. So that is RA HA, and then you have 50 kilonewton, and then you have 40 kilonewton, and since C is a pin, we have 2 forces. So we have 2 forces. So these 2 reactions, we can mark them as RC and HC, and then we have a vertical component, and that has RD, HD, and then you have HC and RC, and then the load, uniformly distributed load of 15 kilonewton per meter. So now let us see whether we can solve this. So here we have 4 unknowns where HA is equal to HC, and other 2 unknowns are there, and then if you balance vertically, you can balance RC and RA equal to 90, and then if you take moment, again we'll have this HC component. So we have to better find it out in this component, that is from CD. So if you consider equilibrium of CD, so vertically balancing, you will get RD is equal to RC. Horizontally, you will get it as HC minus 15 into 690 minus HD is 0. And if you take moment by a point D, then RD and HD will cancel off. Then 15 into 6 into 3 is counterclockwise. RC will cancel off because it is acting along this line, minus HC into 6 is 0. So HC now becomes 3 into 15, 45 kilonewton. So once we know HC, from this equation we can find HD. So HD is HC minus 90. So that is 45 minus 90 minus 45 kilonewton. So HC and HD is known now. So if you take it to this equation, if I mark this one as 1, 2, 3, and this one 4, 5, 6, and HD 7. So if you substitute HD is equal to minus 45 in equation 3, you will get RD into 5 minus 50 into 1.5 minus 40 into 3.5 plus 15 into 6, 90 into 1 minus HD into 2. So HD is minus 45 into 2 is 0. So now if I shorten it, so if I solve this, 5 HD is equal to 50 into 1.5 is 75 plus 14 3.5, so 35 into 4 is 140 minus 90, and then this is plus 90, so that's another minus 90. So 140 plus 75 is 215 minus 180. Okay, so that is equal to 20 plus 15, 35. So RD is 7 kilonewton. RD. So if RD is 7, RA is 90 minus RD from equation 1. So 90 minus RD is 7, so 83 kilonewton. So we have found HC, HD, and now we can find HA also if you substitute HD 45 in equation 2. So HA is 90 minus 90 plus HD. So 90 HD is minus 45, so that is 45 kilonewton. So having that, now we have solved all the reactions. So now what we are going to do is we are going to plot CD separately and A, B, C separately. So if you look at CD, so here HC is 45, HD is minus 45, means the other direction, so 45, and the load acting on this. So this is like a uniform distributed beam on the flipped position, 90 degrees flip. So RC and RD are equal. So RD is 7. So RC and RD are going to act like a axial load, and if you look at this one, the shear force is going to be shear force diagram. If you look at it, so 45 and uniform distributed load, and minus 45. Okay, so that is how shear force will look like, and bending moment, since C and D are pin, so it will be 0 here, moment, 0 moment, and this is under tension, this area under tension, this is under compression. So we will draw it on the compression side. So that's what we will use. Opposite tension, always draw the moment diagram positive on the compression side of the member. So the member, it's a uniform, like a uniform distributed beam. So the bending moment diagram will be like this, and this value will be WL squared by 8. Okay. So W is 15 and L is 6 squared over 8. So this is the bending moment diagram and shear force diagram for the member CD. Now we need to look at the member ABC. So if you look at ABC, so we have these reactions already known. So RA is 83 kilonewton, and HA is 45, and then there are 2 point loads, 50 and 40, and then you have RC and HC. So RC is equal to RD, that is 7, 7, HC is, we have found it as 45. Okay, so that is 45. So now B is a fixed joint. A is pin, C is pin. Now in this case, we need to approach like the previous problem, the one we have done yesterday. That is, you break this into 3 components. So the first component is the horizontal beam, where you have this 7 kilonewton, you have the 45 kilonewton, and I will mark this one as RB and HB, and then I'll have a moment, that is MB. The moment comes in because we have a fixed support at B. So what we do is we cut just after B and just before B. So this is our joint. So B. So we cut it. When you cut a beam in the middle, then we know that we expose three unknowns. So this is the joint B, where you will have the opposite HB, then you will have opposite RB, and then you will have opposite MB. Okay, so now we can approach this beam as a separate element, that is BC, and we can approach AB as a separate element. So here again let me mark this unknown, so I'll mark this one as RB1 or HB1, and then RB1, and this is the moment clockwise, so I'll have a counterclockwise moment MB1. Now it's very easy for me to define this, because now HB1 is equal to HB, RB1 is equal to RB, and the moment is equal to MB is equal to MB1. The reason is here it is a joint, and there are no external forces acting here. So what I can do now is I can draw the next part. So it should be a straight line. So 83, then 45, RB1, HB1. This is counterclockwise, means clockwise MB1. So now we can take consider equilibrium of AB. AB. So if you consider AB, if you balance vertically, 83 minus RB1 is equal to 0. So RB1 83 and HB2 is 45. The moment, if you take moment at B, so minus MB1, that is clockwise. These two forces cancel out, this one cancel out. 45 into 4, the distance is 4 meters from B to A. So 45 into 4, MB minus MB, because it's clockwise. This one plus 45 into 4 is 0. So MB1 is 45, 90 and 180 kilonewton meter. So if I want to plot this shear force and bending moment diagram for this MB element, okay, so if you take here HB, so here we have 45, so there's no load, so this is the shear diagram, so let me mark in a different color. That is the shear force diagram. And then if you consider bending moment diagram, so here it's a fixed support, here is a pin, So already we have a moment. So this moment is a MB1 is positive, so it's a clockwise, so it will tend to bend it like this. So this area will be tension, this is compression. So I have to draw on the compression side. So I'll start with 180 and it's going to reduce to 0 because there is no load. Okay, there is no load. So this is the bending moment diagram for A, B. Here was the bending moment diagram for A, B. Now, if you consider the part BC, so consider BC, you have a horizontal element. So here it is 7 and 45. So here it is going to be 83 and 45 Newton, and the point load 50 and 40. Okay, so now if I would draw shear force diagram, so 83, let me draw in a different color. 83, then you have 50, so that is 83, 50 means 33, then 40, 7. Minus 7. So this is the shear force diagram for BC. So if I take the bending moment diagram for BC, it will be a linear curves. So you will have here the moment is, so now if you look at this, MB1 is positive 183, 80. So this is positive, this is positive, this is positive. So positive, if it, this is what's going to happen, this is going to have a hogging moment. So it will bend this beam like that. It tend to bend like that. So you will have a tension on this side, compression on this side. So we'll plot it on the compression side. So you will have 180 positive, and here it will be 0. Then here if you look at this, the steep curve, then to this point and then this point, so it will be so here the drop is 83 and the distance is 1.5 to 1.5. So 83 into 1.5. So that is the difference. So here you have 180, and then 83 into 1.5 is 83 plus another 1.5 of 83, that is if I calculate, into 1.5, it's 124.5. so here the value is 180 minus 124.5 minus 124.5, that is 55 point. So that is 55.5. So there's a sharp drop. Then here it is 33 into 2, 66. So 33 into 2, so that is 66. 55.5 minus 66, that is 10.5. so that is less steep, and here it's going to be 10.5. If you draw it to scale, it will be much less, 10.5. so it's going to be a shallower line, 10.5, and from 10.5 to the value here 0. Okay, so that is 1.5 into 7 is 10.5. so that is, so this is the bending moment diagram. This is shear force diagram. So if I merge these three, if you look at this, if you look at the shear force diagram, we have, this is the shear force diagram of a vertical member. Then if you combine this, this is the shear force diagram of the horizontal member. Then this is the shear force diagram of the vertical member CD. So similarly, you can combine bending moment diagrams as well. So when you combine all these three, you will get the shear force diagram and bending moment diagram for the frame. So if you look at the second example, I'll explain you how to do this, but we are not going to do this. If you look at shear and moment diagrams for each member of the frame, if you look at A is a pin, B is a pin, and C is a pin. So we have to cut it. We have to, if you cut it at B, since it's a pin, we can cut at B. We don't need to cut it before and after. That's no need. If it's a pin. So if you remove this, then you will have two reactions: horizontal, vertical. Here you have vertical. Then you can plot this one. It's very easy. Then using these reactions, you can plot this one. you may have done a lot of problems with the triangular load acting on a beam. So this is same as that, but here the only difference is it is in a slope. So overall, what you have seen in this frame analysis, so analysis of determinate frames. First, find the support reaction. support reaction. Second, you have to see if you can separate the elements. So that means as we have separated here. Now even if you have fixed support here, it would have, you know, if C and B are fixed, then we should have one roller to solve this. Otherwise we will be in a difficult situation to analyze. For example, if you have C also fixed joint, B is fixed joint, then what will happen is we can't cut it here. When you cut it, you expose more unknowns. Then you can't solve. So in that case, I would have one of this as roller. So if I have a roller, then I can find this external reaction. Then when I cut it, I'll have three unknowns which I can find. And then I can cut it here and cut it there. So even if it is fixed, we can solve, provided one of this A or D is a roller. But so that's what we need to look at. We need to see how can we separate the element, then solve, analyze each element. Okay, so element. You can also go through the book and then do more problems. Say if you look at the book, analysis of frames, trusses, so see here, you know, when there is an element like that, they cut it like this, and the joint is handled separately. This is a problem we looked at in the morning. Okay, so we have a shear force and bending moment diagrams. So you can we can see our work, whether we made any mistakes. That is so this book is on the other side, so that is a sign convention. And you can see the shear force diagram and the bending moment diagram. So okay, so this is the bending moment diagram. So we have to you can practice more problems from the book and be familiarized. So this is the problem that we have done now, and this is the next one, so you can try yourself and familiarize with the subject. So this is how we analyze frames. So under internal loadings, moment diagrams, and shear force diagrams for a frame. So this is statically determinate frame. Okay, not statically indeterminate frame. So you can work out some more problem and then familiarize. So, and there will be a quiz next Monday So I will upload the quiz to the course web. So you will we have a lecture, I think this is your timetable. So we have a tutorial hours 1:30 to 2:30. So your quiz will be available from 1:30 to 5:30. Sometimes I'll give more time, so you can work out that and submit online on the course web. So that's the quiz on next Monday. That is going to be on 11th July. So familiarize with the subject of uh, frames, that is statically determinate frames. So next week we will start with cables and arches. Okay, so next week cables and arches. If you have any questions so far in this, you can write to me to my email not Gmail, it's late. And my mobile WhatsApp. Okay, so you can watch a couple of times these videos and then familiarize. And we'll stop here, and I'll meet you with cables and arches next Thursday. And also there will be a quiz on Monday that you have to do on your own and submit. Thank you.